Hey, welcome back. Today we're going to be talking about a property of some transverse waves called polarization. So I want you to take a look at this picket fence here, and I want you to imagine for a moment that there is a rope that has been tied through the picket fence and it has somehow been attached to a rock on the backhand side, and it's going to pass through this slot right here in between the slats for the picket fence, you could say. Alright, so this rope is tied on back here, and let's say I move the rope like this in this plane. Most of that wave action would be blocked when it got to the slats for the picket fence, right? Let's say on the contrary, I took the rope and I moved it in this plane right here, back and forth, oscillated it back and forth, and at least some of that wave energy, that wave action would pass right through because it wouldn't be blocked unless I went too high or too low or a little off to the left or the right. But let's just say I was moving like this, a fair amount of that wave energy would pass through. And that's the concept we're talking about today. So some waves can be polarized. They can be blocked by a polarizing film or a reflective surface, and as a result, only waves in some orientation can pass through a polarizing surface. So that's what we're talking about today, so let's go ahead and give it a shot. Alright, here's another visual that will help you to understand what we're talking about. So you could say, imagine there's an axis right here, so this is a device that's whirling waves around in a circular manner. These waves are on some sort of string that's attached with tension over here, and then there are very strong barriers that are in this plane right here. And so we have waves that would be in this axis, waves that would be in this axis, this axis, this axis, every imaginable axis in 3 dimensions, you could say, with this line being the axis and this being roughly the center right here. But if you notice, only the energy that's in this plane can pass through. And so as the wave energy passes from this side over this side, we would say this wave over here is polarized. So if you can visually see and understand that this is all in one plane, a transverse wave that's all in one plane, that's what we mean by a wave being polarized. So to officially define it, we'll say linear polarization is a property that can apply to transverse waves where the amplitude of the waves is all in one plane. So this is a polarized wave over here. We're going to talk about this not just for like mechanical waves, but in the context of EM waves, where the electric field is going to be the transverse wave that's going to be polarized like this. Alright, so let's think of an EM or an electromagnetic wave. So before in the past I've drawn something kind of like this. Now I will say at the outset that some of these visuals are a little difficult to draw and to visualize. Hopefully you get the idea. Fundamentally, we're talking about 3 dimensions on a 2-dimensional surface. So this is in the x-axis, this is the y-axis. Here we're going to call the z-axis, and I'm going to argue that the y is at a right angle to a z, although it's a little hard to see from our perspective. Alright, so to make this easier to deal with, let's go ahead and just focus on the electric field for now. So the magnetic field is going to follow, it will always be along with the electric field essentially for EM waves. And for our purposes, we can kind of ignore it for now to simplify the drawing. If you have a polarizing film, so first of all, this is what I mean by a polarizing film over here or over here. They're like cheap plastic, they're fun to play with in a physics class. I'm going to represent that, it's almost like our picket fence, you could say. I'm going to represent that first with a drawing kind of like this to give you the idea that, yeah, if the waves are in the y-axis here, they will be able to pass through completely. This would be like having a rope pass through a picket fence exactly in the same plane as the slats in the picket fence. And to make life even easier, I'm going to simplify this drawing and just represent it with a larger line down the middle that shows the direction of the plane that we're working with. So I'm going to go ahead and take this whole drawing and simplify it with this down here. Alright, now based on that, most light that we deal with in our everyday life is unpolarized light. So you can see here that we've got light that's going to vibrate in every direction for its electric fields. As it moves along the x-plane, it's going to vibrate in the y and the z in every direction, you could say. But with this polarizer set up this way, it only allows light in this axis to pass through. So we could say only the percentage of the light that is vertically polarized would pass through. That's in the vertical plane, you could say, would be allowed to pass through. Now I want to ask a question. It's a little hard to see this, but are the y and z axis at right angles to each other? So check this out. Are these at right angles to each other? And the answer is yeah. It's a little hard to see that, but these are at right angles to each other. And so if our electric field is going to be coming in like this for a wave, it's going to hit a polarizer that's going to be in this plane, this Z plane right here. My question is, how much of this wave energy is going to pass through the polarizer? Well, essentially none of that wave energy would be able to pass through. The polarizer is in a different axis, and so it's going to block that wave energy from passing through. It's kind of like saying, if you have a force vector completely in the y-axis, how much of that is in the x-axis? Well, the answer is none of it is, right? It's completely in the y-axis, none of it is in the x-axis, so it's not going to be allowed to pass through in this case. Okay, well, let's give a more real-world example. Since most light that we deal with starts out as unpolarized light, like light from the sun or light inside a room, it's going to be unpolarized. And so what happens if that light passes through a polarizer that's in the y-axis? Well, that's just going to allow this light that's now polarized in the y-axis to be able to pass through. And then let's say we have another polarizer in sequence after that. So we have two polarizers in sequence, and that's going to be in the Z. How much of that light is going to be able to pass through? Well, the answer is none of it, essentially. If the polarizing films are at right angles to each other, then you could say it only allows light from one axis to pass through the first polarizing film, and then none of that light can effectively pass through the second one. So if you have two polarizing films at right angles to each other, where they overlap, you're not going to get any light passing through. Alright, and so before we do move on, I do want to mention a very important concept. We're going to come back to this later, but what is the cause of an electromagnetic wave? That's going to be if you have a charged particle that's accelerating. So like an electron that bounces up and back down, or repeatedly bounces up and down, that's going to send off waves of electric fields. And again, we'll talk in more detail about all of that later on, but if you can get that concept now while we're talking about electric fields, then that will make life easier for you later. Alright, and I think I'm going to break this lesson up into two parts, otherwise it's going to be too long. So the second part of this lesson is coming right up. It's going to be on sunglasses, so applications of polarization, as well as circular polarization. So please stick around. There should be a link in the upper right that you should see soon. Thanks for listening. Have a great day.